Hello everyone, my name is Arash Amini. I'm a master student at University of Bonn in Autonomous Intelligent Systems Group. I will present our work T6D-Direct Transformers for Multi-Object 60-Pose Direct Regression. 60-pose estimation determines the 3D translation and 3D rotation of an object in camera-centered coordinates. This task has a wide applications such as robotics, autonomous driving, and augmented reality. In this task, we need to handle occlusions, symmetries, and textureless objects. Moreover, the scalability and inference time of the proposed method are important. Object pose estimation from an RGB image can be broadly classified into the three categories: direct, indirect, and refinement-based. Direct methods regress the translation and orientation components of the object pose directly from the input image. Indirect approaches recover the 60 pose from 2D-3D correspondences using PMP algorithm, where PMP is often used in combination with RANSAC. Refinement-based approaches formulate the 60 pose estimation as an iterative refinement problem. Since indirect methods depend on PMP algorithm, which is computationally expensive, we opt for proposing a direct method. Recently, transformers equipped with the multi-head self-attention mechanism are emerging to achieve state-of-the-art results in many computer vision tasks. For instance, DETR introduced an end-to-end differentiable object detection pipeline using transformer in combination with a CNN backbone model. DETR formulates object detection as a set prediction problem. The model takes an image and generates a set of tuples with fixed cardinality, where each tuple consists of bounding box and class probability of an object. Inspired by that, we proposed T6D-Direct, a direct single-stage method for multi-object 60-pose regression in real time. It has an end-to-end pipeline where it estimates all object poses in one forward pass. The proposed model has 5 components: backbone, positional encoding, encoder, decoder, and finally prediction heads. In the next slides, I will explain each component in detail. For backbone, we use a ResNet50 model with the frozen batch norm layers pre-trained on ImageNet as a feature extractor. We reduce the dimension of extracted feature maps to 256 using 1x1 convolution and flatten the features into the 256 times HW feature vectors. Transformer architecture is a permutation invariant. Therefore, to give the model some information about the relative position, we used fixed sign positional encoding. The equation of the sign positional encoding is shown on the right corner, where D is the 256. The sum of feature vectors and fixed sign positional encoding are passed through the encoder. Each encoder layer includes a multi-head self-attention with query, key, and value of size 256 and a feed-forward network. Decoder takes output embeddings of the last encoder layer and n positional embedding, where n is the cardinality of the prediction set. Using a standard multi-head attention mechanism and learnable positional encoding called object queries, the decoder generates n query embeddings. From n decoder learned positional encodings, we use feed-forward network to generate set of n output tuples. We choose n to be larger than the expected number of objects in the image and pad the rest of the tuples in the set with no object. There are 4 feed-forward prediction heads to predict the class probability, bounding box modeled as a center and a scale, translation, and orientation components of 60 pose independently. Each feed-forward network is a 3-layer MLP with hidden size of 256. Among the existing rotation representations, to predict the orientation, we employed the 60 continuous representation, which is the best fit for neural network in practice due to its continuity. We compute the 60 representation based on equations provided in the slide. We perform bipartite matching to match the predicted set y hat by our model with the grant-to set y. We search for the permutation of elements between these two sets sigma that minimizes the matching cost. The matching cost has 2 parts: the cross entropy loss for class probabilities and the bounding boxes loss. The bounding boxes loss is a linear combination of generalized IOU and L1 loss. In the next step, our model is trained to minimize the Hungarian loss for R pairs matched between the predicted and grantor sets. The Hungarian loss consists of three losses: cross-entropy loss for class probabilities, bounding boxes loss, and for post-estimation, we utilize the symmetry error loss for rotation and L2 loss for translation. We evaluated our method on a large benchmark YCB-Video Dataset, including 21 YCB objects captured in the 92 videos from cluttered indoor scenes. This dataset is challenging due to the occlusion and symmetric objects. We present the per-object post-prediction results on a YCB video. Our method and post-CNN are both direct methods and comparable, while PVNet is an indirect method and DeepIM is a refinement-based approach. Our model outperforms both CNN and PVNet for both metrics and achieved the fastest inference time. For the Ablation Study, we investigate various loss functions and different training strategies. Single-stage training with the symmetry error loss and egocentric rotation representation achieves the best ADES result, while using the symmetry error version of the point matching loss with L2 norm, which couples the rotation and translation components, resulting in the best IUC of ADES. We also depict some predictions from the test scenes. We can observe that our model post-predictions are considerably better than post-CNN. To understand how transformer works for the task, we visualize the encoder-decoder attention maps. We can observe that transformer can localize each object and separate them successfully in both encoder and decoder modules. We visualize the encoder self-attention maps for 3 pixels belonging to the 3 objects in the image. All 3 pixels lie on the same horizontal line but attend to the different parts of the image. In this work, we propose T6D-Direct, a real-time single-stage transformer-based architecture to tackle the multi-object 60-pose estimation task. Our model obtains competitive results compared to the state-of-the-art methods and running at 58 frames per second. Our model is ideal for real-time applications. For future work, we plan to take advantage of dense features in our model. Thank you for your attention.